to determine whether or not this series converges, the most straightforward test to use would be the ratio test. The ratio test is often useful when we have nth powers of some number. Here's the ratio test for your reference. Recall, we're going to have to look at the limit of the magnitude of the ratio of consecutive terms of the series. If that limit is equal to some number that's less than 1, then our series is absolutely convergent, which also means it's convergent. So, applying the ratio test, we're looking at the limit as n goes to infinity of the absolute value of the n plus 1th term of the series divided by the nth term of the series. So the numerator is found by just taking a term of the series and plugging in n plus 1. So we have n plus 1 squared and 2 to the n plus 1. And then the denominator is just the nth term of the series. The -1 we're totally ignoring because this is in absolute value bars. The ratio test requires us to use those absolute value bars, which means the -1 does not matter. Again, it's just the n plus 1th term divided by the nth term. Now we can do some simplifying. Dividing by n squared over 2 to the n is the same as multiplying by 2 to the n over n squared. So n squared is going to be in the denominator, and 2 to the n is in the numerator. We also, of course, have n plus 1 squared in the numerator, and 2 to the n plus 1 in the denominator. Now, we have n factors of 2 in the numerator because of the 2 to the n, and n plus 1 factors of 2 in the denominator. So all of those 2's will cancel out, except for 1. There will be one factor of 2 left in the denominator. Thus, in the denominator, we would have 2n squared. In the numerator, we canceled out all those 2 to the n's, and then we would have n plus 1 squared, which is n squared plus 2n plus 1. And you should know what this limit is equal to. The absolute value's not doing anything since everything here is a positive integer. In the numerator, we have a polynomial of degree 2, and in the denominator, we have a polynomial of degree 2. Since the variable, n, is going to infinity, the limit of the ratio of these polynomials of equal degree will just be the ratio of their leading coefficients. The leading coefficient in the numerator is 1, the leading coefficient in the denominator is 2, so the limit is equal to 1/2. In the context of the ratio test, what's important about the limit being 1/2 is that it's less than 1. And of course, the ratio test tells us that if this limit is less than 1, then our series is absolutely convergent. So, indeed, our series is absolutely convergent, which also means the series is convergent. Remember that being absolutely convergent means that the series would converge even if we took the absolute value of each term. So the original series without the absolute values will have some of these negatives canceling it out, and thus that one is definitely going to converge. Remember, the series being absolutely convergent means that it would even be convergent if we took absolute values of each term. So without the absolute values, it's definitely convergent because some of the terms will be negative and cancel out with some of the positive terms. So that's how to show this series is convergent using the ratio test. Let me know in the comments if you have any questions, and be sure to check out my Calculus 2 course and Calculus 2 exercises playlists in the description for more. Thanks for watching.